Hi, folks. Welcome back. I hope you're all doing well. The paper I'm looking at today came out just a week ago, but it was a few days before the release of the latest GPT-o1 model. And the results of this paper would have been very different, would have been better with that model. And I bet the authors are already looking into that. But all the same, even with the now old models, this paper has some very interesting results. So, as the title says, they're trying to use language agents to get superhuman synthesis of scientific knowledge. And by this, they don't mean creating new scientific knowledge, but being able to understand and summarize and answer questions about a large body of existing scientific knowledge. They're looking at 3 tasks that are a huge chunk of any modern scientist's or researcher's workflow. The first one is retrieval and understanding. So you have to read and understand a large body of existing literature and be able to answer questions about it. Once you've done that, the second task is to summarize and synthesize a report or a summary which can cite all the relevant sources correctly and back up all the claims within that summary. And finally, when your understanding is deep enough, you want to be able to detect contradictions within the existing body of work. Old papers might have their findings changed or annulled by new discoveries, or the scientists might have made a mistake and introduced contradictions. So you want to have an understanding deep enough to know where those contradictions lie. So these are the 3 very specific tasks they're looking at. And the way they do it is by creating an agent system with LLMs that they call PaperQA2 that is specifically tuned for these tasks. This is the overall agent architecture of the system. There's things like paper search to search over the existing body of literature. There's a RAG setup which chunks up the raw material, puts it into a vector database, but it's set up in an agentic way. So this is not traditional one-shot RAG. They do things like re-rank and summarize the chunks that match, and then they take the top scoring summaries to finally synthesize an answer. They also have a component that does citation traversal, so looking at all the papers that are cited by a given paper and then looking at those cited papers. And finally, after all that, they generate an answer. So whenever you design a system like this, you first have to ask, well, how are we going to evaluate it? So one of the big contributions of this paper is a benchmark. The authors made a benchmark that they call LitQA2, which has about 250 multiple choice questions from the scientific literature. And they picked these questions in a way that the answer appears in the main body of the paper, so not just in the abstract. And it's only in one paper. So if the answer appears only in one given paper, it's much easier to check the correctness or to evaluate the correctness of the system after the fact. And what are the metrics they're looking at? So the traditional metrics for retrieval systems are things like precision and recall. There's one additional twist here, which is that sometimes the system might refuse, saying there is insufficient information to answer this question. So they look at precision, which is when a response is provided, what fraction of those answers are correct. And then accuracy is a fraction of correct answers over all questions, so that includes the refusals as well. And here's the interesting thing that makes the evaluation of this really good and different from a lot of other papers. They found human annotators who were pretty advanced in the field, either had a PhD in biology or related science, or were enrolled in a PhD program. And they were paid between $3 and $12 per question to answer as many questions within a span of a week. So that's a pretty stark comparison. So here's an agentic RAG system being compared with either PhDs or advanced graduate students that were paid to answer these things and could take up to a week to answer them. And here's the headline result that justifies the use of the word superhuman in the title of the paper. On precision, the human evaluators scored about 64%, whereas the paper QA2 system got 85%. And on accuracy, the humans got about 63%, while the paper QA2 system got 66%. Now, if you try to break down the factors that led to that good result, there were a couple of key ones. One was citation traversal. So this graph shows that citation traversal alone provides a big boost to recall. The other big technique that helped was this re-rank and summarize technique. As the authors mention here, having a list longer than 10 among those re-ranked and summarized chunks, along with a high-performing frontier LLM, was one of the crucial factors in achieving superhuman performance here. So now that you have a retrieval and synthesis system, an agentic RAG system essentially, the next step after that is to take the replies from that RAG system and try to synthesize a very detailed summary. And that's exactly what they're doing in step 2 of this paper. They try to generate cited Wikipedia-style articles about a very specific topic, protein coding genes. And again, here's the interesting part. They're using real human evaluations. They measure it with human-written Wikipedia articles, and the comparisons are done by human subject matter experts. Here you can see how one topic breaks down into several calls to the underlying paper QA system, and the replies of those calls are finally synthesized into a finished article. This table shows a comparison between existing Wikipedia articles and the articles generated by this system. As you can see, the average length is a good deal longer than the Wikipedia human-written articles. And here's the interesting part. So the accuracy, which looks at, of all the claims made within that body of text, how many are cited and correctly supported by those citations. Wikipedia only had about 60%, whereas this WikiCrow system gets about 83%. The inverse of that, which is to count how many was cited but unsupported, which is to say that the citation was not correctly used. We see that the system here has a much lower fraction of those, nearly half at 13.5% versus 25% for human written articles. Another interesting thing here is to look at the specific reasons for unsupported citations. And citations could be unsupported because of several issues. It could be a reasoning issue or an attribution issue. And again, you see that the WikiCrow system here has a much smaller occurrence of those issues. And that brings us to task number 3 in this paper, which is to detect contradictions in the existing body of work. The way they do that is to first extract claims from the papers using LLM prompts, and then give those claims to the paper QA2 system, the agentic RAG system, with a specific prompt for contradiction detection. And the output of that prompt isn't a yes-no decision on whether there is a contradiction or not, but rather it is a scale which scores how likely that claim is to be a contradiction. So as you can see in this diagram, they use an 11-point scale going from explicit agreement all the way to explicit contradiction. And they're considering anything at 8 and above to be a contradiction. And the system they have achieves an AUC of 0.8, which is to say it has both pretty high precision and high recall. Now, this graph over here tells you of all the contradictions that the system found, how many did human evaluators agree with? And it's about 70%, which when you look at these kinds of systems where you try to find agreement between human evaluators and systems, that is a pretty high degree of agreement between the two. And the average contradictions per paper was about 2.3. So it did find a fair amount of contradictions in this body of work. All right, so that was a quick look at a paper that correctly claims to have built an agentic LLM system to get superhuman performance on some of the most common tasks in a scientist's workflow, to understand a body of knowledge, be able to answer questions about it, synthesize summaries out of it with correct citations, and finally to understand it deep enough to identify contradictions within that body of work. And on all these three tasks, this system was evaluated against human experts and judged by human experts, and still demonstrated performance better than those human experts. So that is a really interesting result. I hope you enjoyed that, and if you like content like this, please like the video, consider subscribing, and I will see you all next time. Thank you very much.